मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
Before we proceed with our quadrilateral quadratic elements, let us just go and look at what we did before that. Okay, I had just left it vague, this triangular element, the 6-noded triangular element. I left it vague deliberately because I wanted you to look at it and see whether you can develop it. And now I know that many of you have not done it because it is, you have to put in some effort, okay, and maybe still things have not crystallized. So let us go back and have a look at as to how to develop this Dn matrix. Okay, I know that the problem is in the development of Dn, because once you develop Dn, I am sure that the rest of it follow quite easily. Is that clear? So I just want to go back and tell you as to how this can be solved. Now let us see what are the difficulties. Okay, initially we had, I hope all of you are now clear about psi 1, psi 2, psi 3 coordinate system, right? Is it clear? Is there any doubts? Yes, is there any questions on that? Okay, so you know psi 1, psi 2, psi 3 coordinate system. That is the first thing I did, right? And then this was followed by I writing down n1, n2, n3 so on in terms of psi 1, psi 2, psi 3 and so on. Okay, they are quadratic in nature. I have written down such a fashion that our shape functions are satisfied and so on, I mean properties are satisfied and so on. The next thing I did was to define psi eta, okay, with which we are familiar with, okay, which is easier to do in a natural coordinate system, because we also pointed out that psi 1, psi 2, psi 3 are not independent, and psi 1 plus psi 2 plus psi 3 is equal to 1, and hence we said that let me call psi 1 as psi, psi 2 as eta, and psi 3 is equal to obviously 1 minus psi minus eta. Okay, you can retain psi 1, psi 2 and 1 minus psi 1 minus psi 2 and call psi 1, psi 2 as the psi eta. I did this because psi eta are the two coordinate system, so I wanted to develop it in the same language, that is all, nothing more than that. Okay, so because I have to introduce this, they are not independent, okay, they are dependent, that is what I did. Okay, so after doing this, I wanted to calculate the J matrix, right. Now what is that I need? I need to substitute for x in this equation. What is x? Ni xi. Is that clear? Okay. Now look at these things, I have put psi and eta. So I think the major difficulty, if I understand from you, is how to calculate it in psi and eta, because I have written all the n's in terms of psi 1, psi 2 and psi 3. Okay. Now this is a very simple thing to do. Is that clear? Is that the question, right? It is very clear, because psi 1 is a function of psi. So if I want to write down, say dou ni by dou psi, what I do is very simple. This is equal to dou ni by dou psi 1 into dou psi 1 by dou psi plus dou ni dou psi 2 into dou psi 2 by dou psi plus dou ni by dou psi 3 into dou psi 3 by dou psi. Is that clear? Okay. So that's it that you have. Now how do I calculate psi 1 dou psi 1 by dou psi? I have the relationships here. So dou psi 1 by dou psi, this becomes 1, dou psi 2 by dou psi becomes 0, and dou psi 3 by dou psi becomes minus 1. Is it clear? So essentially dou ni by dou psi becomes now dou ni by dou psi 1 minus dou ni by dou psi 3. Is it clear? So once I have this, okay, my entries in Dn becomes very straightforward, right? Okay. Now there are two ways in which Dn can be written. Again, I am not confusing, but I am trying to say that these are very logical things. There is nothing very difficult about it. Say for example, I can write down the same j as dn, okay. After all, what are these? This is I am going to substitute here for ni xi, okay, here ni yi. I am going to substitute these two things there, ni xi and ni yi. So I can look at these xi's and yi's. What are they? x1 x2 x3 y1 y2 y3 as a matrix x3, I mean x1 x2 x3 x4 x5 x6, okay, if you want to complete it, as a 6 by 2 matrix as well, right? I can write it down like that. And then what is the size of dn? 2 by 6, okay. So 2 by 6 into 6 by 2 will get the 2 by 2 matrix. See, these are all the ways. See, this, it is very important that you know how you can manipulate with it, especially when you want to develop a code. These kind of things will be very useful. Yes, you can write this down as 12 entries, okay, x1 y1 x2 y2 x3 y3 x4 y4 and so on, right? As a vector you can write down. Then dn will correspondingly change, okay. That will become a confusion. No, that would not be very easy, whereas here this is it's easier to write. Is that clear? Okay. So 2 by 6, 6 by 2 will give you a neat, then you have to calculate differently, separately, then add it up and all that kind of thing you have to do. Okay. Now having done this, I want you to tell me what is dn. Have this in mind and let us see how many of you are able to calculate dn, okay, right. So can someone calculate dn for me and tell me, have these things, okay. Now calculate dn. Is there any questions? Let me stop here for a minute because I think one or two of you said that we need some clarification. Is there any other question which is there? Yeah, any questions? Is it clear till now whatever I am doing? Okay, then in that case you should be able to calculate dn, okay. Let us see whether you are able to calculate dn. Yeah, have a look at these things. All these things should be in your notes, so just calculate them. What is the first entry? Dou n1 by dou psi. So what is dou n1 by dou psi? Look at this. One minute. dou n1 by dou psi is dou n1 by dou psi 1 minus dou n1 by dou psi 3. The second term goes off. So, I mean for this n1, so that is same as this. So, that is equal to 4 psi 1 minus 1. That is all, very simple, right. Okay. Now, what is your next entry? 0, and fantastic. What is your third entry? 1 minus 4 psi 3, right. 1 minus 4 psi 3 and so on. I am sure now you will be able to fill it up, right. Okay. So, here again 0 and so on, and here again you have to put 0, 4 psi 2, just fill it up. Okay. Now, once you do this dn, then the procedure is exactly the same. You know, the procedure of doing it is exactly the same as what we did before. Is it clear? Okay. In other words, what is that we do? Now we find out psi 1, psi 2, psi 3. So what happens here? Now this becomes a function of psi 1, psi 2, psi 3 and so on. Okay. Now what is that you do? You substitute this in k, okay, and then do the integration, right, area integral straight away, right. Now when you do that area integral, the procedure is exactly similar to what we did before. We have some sampling points, we have some weights. So at these points we have some weights. So calculate this P transpose dBj, okay, what we have there at those sampling points, multiply by weights, right. So suppose I write that, say for example phi dA, that is equal to sigma wi phi I ji. Many textbooks what they do is to put a half due to certain reasons, let us not get into that, and then give the weightages, okay. That is because of the area calculation in the natural coordinates, but nevertheless this is how many textbooks also write. But if this half is not there, then it should be in the weights. So this half, many people put this half and write it like this. So you calculate whatever is there in this phi, like what we did for the quadrilateral element, same fashion, okay, calculate it, get the stiffnesses. Now it is not, please note the difference here. There for a 2-dimensional element we did 2 summations I and j, 2 into 2, right, but in this case the quadrature points are very well given, okay. And as I told you, refer to any of the standard textbooks, okay, on these issues, okay. That is an exercise, that is one of the assignments that I give you. Please go and have a look at the chart of a book, then you will know how this is calculated. Is this clear now? Any questions? Okay, how all the steps are done? Okay. Now if it is clear, let us get back to our higher order elements with which we started work. Now I am going to go into details of certain very interesting things today, okay, very practical things as well as very important things. Now before we proceed to, and these practical and important things are based on the integration rules. Remember we had already talked about the integration rule, just touched upon it. There are a lot of very interesting and important things that happen in the integration rule. But before we go further, okay, let us look at that shape functions once more. Let us look at the shape functions once more. Now as someone pointed out in the last class, see after I put down it became simpler for you to write it down, but before you put down you are not hard pressed to write down the equation. That's what a very nice comment which was given last class. But now I will tell you that you can write down yourself. Okay. How do you write down? Let's see. I'm sure many of you would write down now the shape functions for an 8-noded element. Okay. Why am I asking you to write down? Because the whole idea is once you write down, you become very familiar with the subject, okay, as to how things are written. Okay. In fact, you can develop a code. That's the ultimate, okay, in finite element analysis. Okay. Let's now look at 8-noded elements. Okay. 1, 2, 3, 4. Look at the numbering. It's always done like this. Okay. Psi eta coordinate system. Remember that we developed the shape functions for our 4-noded element by looking at what? The 3 methods which we did: inspection, then Lagrange interpolation. We did one more thing also, line. Very good. By looking at the equation of the line and seeing whether that particular point falls on that line or not, right? Get back to that, just have a look at it. For example, we said that, okay, forget for a moment 5, 6, 7, 8, okay, just see that, say that there is only 1, 2, 3, 4, okay. We said that I have to, when I write the n1 here, okay, I have to eliminate those 2 lines here. So what did we do? So we said that n1 should be a function of some c into 1 minus psi into 1 minus eta, because psi is equal to 1 and eta is equal to 1 are the equations of these 2 lines. So once I put it, because this node does not lie in these 2 lines, so once I put it, automatically when I substitute psis and etas for these nodes, okay, since they involve the equation of the line in which they sit, obviously it would go to 0. Did I say that? I hope all of you understood it. Very nice. Now, can you use the same method to develop shape functions for this element? I will give you 1 minute to think about it. Okay? Fantastic. So I have eliminated by writing this, okay, by writing it like this. First of all, I have, suppose I write it like this, I have eliminated the nodes. What are the nodes I have eliminated, or in sense I have taken care of within brackets, taken care of or within quotes? 2, 6, 3, 7, 4. I have taken care of them, but I have not taken care of 5 and 8. So I should multiply a line, an equation of a line which passes through 5 and 8. Is that clear? Okay. Now just have a look at that and tell me, how do you now write that down? What's the equation of this line? Yeah, correct. So in terms of psi and eta, how do I see psi is equal to 1? I have brought this side. So psi, where do they cut? Your a is what? -1, b is -1. So x by a plus y by b is equal to 1. Now what does that equation become? 1 plus psi plus eta. Fantastic. So 1 plus psi plus eta. So what do I do now with this? I multiply it, that here, 1 plus psi plus eta. Very good. So now tell me, by using our regular properties of shape function, how or what would be the value of c? -1/4. Beautiful. Okay, -1/4. You would notice when you multiply, that is exactly similar to what I did in the previous class, right. You can do that in a very simple fashion. So you write down now n1. Is it clear? Any questions? So what I did was to write down all the equations of all the lines through, I mean, for other nodes, right, and so calculated then C. I can do the same thing with n2, n3, n4. Okay. The only thing I should know is the equation of this line, that line, that line. Once I know the equations of these other three lines, I can calculate n's, n2, n3, n4. Now let us see how I am going to write down n5. Let us see. Now any questions? 2, 3, 4 is clear. n5. How am I going to now write down n5? Yeah, note this n5. Okay. Now, yeah, come again. Enter 3 lines. Beautiful. So that is C into, what are the equations of those lines? 1 plus I into 1 minus I, 1 minus eta. Remember, what is C? Half. Get back and see what we did in the previous class for n5. You will see that that's what you get, right. So this is a simple method to understand also how to develop shape functions, right. So n1 to n8. Okay. Now I am leaving the rest of it for this higher order element as an exercise, calculation of dn and so on. Okay. We can later in a class, maybe in a tutorial, we will do that, but I would like you to complete the picture. Okay. I would like you to complete it. If there is any questions, you are not able to do it, tell me in the next class or after that, right. Okay. Now we will move to an important topic of numerical integration. Right. I hope all of you remember numerical integration, what we did, okay, before. And one of the important rules, of course, numerical integration had existed, independent of finite element. We call this as Gauss quadrature. We also said that there are a number of ways in which numerical integration can be done. Newton cotes, okay, is one such another formula, and in fact Newton cotes is used in certain shell elements because of certain advantages, okay, but extensively Gauss quadrature rules are used in a finite element analysis. We saw that, and also we said that this is a rule to integrate, okay, say for example a polynomial, and it is possible to arrive at a exact integration rule. What is it? 2n minus 1 integration points would integrate a polynomial of degree n. So this maybe you know it already, that 2n minus 1 integration points would integrate a polynomial of n. Okay. Now this is what we call as exact integration. Okay, this is what is called as exact integration. But there are a lot of peculiarities to it. A lot of things are played. For example, if you look at a nice element like this, okay, remember that the powers, okay, the polynomials of psi and eta may be present in, there are, what are the terms that are involved in K? B transpose D B did J D psi D eta, okay. B transpose D B did J, determinant of J. These are the terms that are involved. Psi and eta can sit in these guys, okay. Certain times, of course, J may become a constant in the throughout the element, okay. Some of the nice things, that nice elements, it may become constant, but certain times it will not be a constant, okay. So you have to know what exists in each of them, so that you will know what is the order of the polynomial and then use the exact or the correct integration rules, right. So for example, this element, I can tell you that the usual, our 2 by 2 rule is used, okay. The rule that I am going to use is a 2 by 2 rule. On the other hand, if I use an 8 noded element, usually a 3 by 3 rule is used, okay. There are 3 Gauss points on one direction, 3 on the other side. So 3 by 3, the totally there are how many Gauss points? 3 by 3, 2 by 2 is 4, 3 by 3, 9 Gauss points are there, okay. We will look at two things. One is, okay, what happens when we do not use 2 by 2 Gauss points, say for example this problem, okay. What happens, or in other words, let us say that the recommended integration rule is 2 by 2, okay, and we use what is called as reduced integration, and we say for example use an integration rule only at the center, okay, 1 by 1 integration rule. Let us say that we are using 1 by 1 rule instead of 2 by 2 rule. When I use this kind of rule from 2 by 2, when I reduce it to 1 by 1, then I am indulging in what is called as reduced integration procedure, okay. Reduced integration. Okay. Now when I use reduced integration, what is your comment immediately? What can be your comment? You are doing something totally wrong, right? You are not following the procedure and you are doing something totally wrong. But there are very interesting things that happen. What are the interesting things that happen? When I use a reduced integration point, the first thing I immediately gain, okay, forget about anything else. What is that I gain immediately, or why am I looking at first of all 1 integration points instead of 4 integration points? One thing I immediately gain, computer time, cost, period, first thing, because I need to now calculate it only at one point, okay. Number 2, what is the other thing that happens? That is a difficult question to answer. Now for that we have to understand finite element, okay, whatever I have done so far in a proper perspective. After all, in finite element, what is that we did? We broke down an infinite degrees of freedom into a finite set of degrees of freedom. So in that process, what did we do? We stiffened the structure, okay. We said that look, you can't have all your infinite degrees of freedom, you can have only finite degrees of freedom, okay. The structures have stiffened, okay. Interestingly, when I go down from 2 by 2 integration point to a single integration point, okay, the structure or the stiffness softens, the stiffness softens, okay. On one hand, it is stiffened by discretization. On the other hand, when I go to 1 by 1 rule, okay, that error is on one direction, okay, I introduce another error in another direction, the structure softens. So it so happens that this error, though I know it is an error, tries to compensate for another error which I have introduced due to discretization, okay, and hence ironically gives better results many times, I mean with a warning, okay, ironically gives better results. So in other words, what is that you are doing, or what is that you are gaining, or what is it that is happening when I go to 1 by 1 rule? 1, I am reducing the cost. 2, I am introducing an error in integration. 3, I am getting better finite element results, right. Basically this is because certain higher order terms, okay, are not integrated at lower, or they go to 0 at lower integration points, okay. So some complex deformations that are introduced by higher order terms are not present, okay, when I integrate it at lower integration points, because these guys are meant to integrate lower polynomials, okay. So if you now look at most of the softwares, they use reduced integration to impress you, because times are very nice, very good, but do you always get good results? Now let us look at what happens, okay, a small output, okay, what happens when I use reduced integration. Let us look at this chart, okay, and see how exactly we get the result. Look at the result, okay. This is a problem where, okay, you have say elements that are defined here and a contact, okay, that is the contact with a rigid body. So of course this problem is a nonlinear problem with contact and so on. Let us forget about that problem for a minute, okay, about the contact and other niceties in this, that we will come to later. But look at the mesh now after deformation. What is that you see in that mesh? The mesh is very jagged, okay. This problem has been done using what we call as reduced integration, and what you get here, this jagged mesh, is what is called as Hourglassing. I will explain Hourglassing in a minute, but I want you to look at the result and recognize Hourglassing. In fact, many students have come and told me, sir, I am getting a result like this, some jagged things. What is happening? So first of all I want you to recognize that if you get a jagged front like this, okay, your mesh is undergoing what is called as Hourglassing. I will explain that in a minute. Now let us look at a proper result, okay, in the next chart. Now that is the actually proper result. The mesh is smoother with a proper integration, and hence, okay, we also land up in trouble by using reduced integration points. Now, so in other words, there are two issues here. One is that we have good results, better results, okay, with 1 point integration, but we also introduce problems of Hourglassing. Okay, problems of what we call as Hourglassing. A Hourglassing, okay, it's actually one word, I shouldn't write it as two words. Hourglassing is known by different names, okay. Sometimes people call this as spurious energy modes or zero energy modes, zero energy modes. People sometimes call them as rank deficiency and so on. Now, what exactly happens, or what is, why do we call it by these names? Why do we call this as 0 energy mode? We call this as, first of all, hourglassing, basically because if you had seen that chart, you will see that the mesh, say, which was like this, sometimes become as if it becomes something like this. Okay, the jagged front gives gives some sort of a impression that an hourglassing is produced. Okay, and hence we call this as an hourglass mode. What do we mean by 0 energy modes? Okay, they please understand that they are very important. Let me just recapitulate what I am trying to say. What I am trying to say is that there is a 2 by 2 rule or 3 by 3 rule depending upon the element, which is the correct rule that has to be applied. Okay, we will again come back to this correct rule in a, later. But before that, we should understand that though there is a correct integration rules, it is possible to follow what is called reduced integration. Okay, people do reduced integration. People do reduced integration because it saves cost. Your software can really rip through, run very fast, number one. Number two, I am introducing an error which is in the opposite direction of the error which I have introduced because of discretization. So my final results are better, nice things that I have, and hence I attempt reduced integration. But things are not as rosy as that, because when I do reduced integration, I also land up in certain other troubles called hourglassing, okay, or what are called as 0 energy modes, okay, or what are called as rank deficiency. All of them mean the same thing, rank deficiency and so on. The name hourglassing comes because of this jagged front that you get. Is that clear? Okay. Before we go to a much more scientific or mathematical explanation, let us understand what we mean by what we call as 0 energy modes. What do we mean by it? All of us know the expressions for strain energy, right? What is it? I can write this down, strain energy as half K transpose, sorry, D K, right, sorry, small d K. Okay, we can write it down as half D transpose, sorry, what am I writing? D transpose KD, sorry, D transpose KD, sorry about that, D transpose KD, okay, there is half K D squared or half K U squared, so half D transpose KD. Now, in other words, strain energy has to be present when there is displacement or deformation rather, okay, and can be absent only when D is equal to 0 or deformation is equal to 0. Okay. Now, strain energy can also be obviously expressed in terms of our epsilon as well. Okay, that is very simple, that is half E epsilon squared. Okay. So hence I can write this as half epsilon transpose D epsilon as well. Okay. So strain energy should be present when strains are present, which are present when deformations are present, obviously. When strains are present, strain energy has to be present. They go to 0 only when epsilon is equal to 0. Now, let us look at one element just near that. Let us look at this element. Okay, just for understanding, it is not very rigorous, but we will do it more rigorously later. But let us say that this element deforms like this. There are other issues in it, but let us not worry about that. Let us say that this element bends and deforms something like this, right? The element bends and deforms like this. Okay, there is, say, compression at the top and tension at the bottom, and so this element becomes like this. Let us say that I am using a 1/1 rule. What am I doing here? I am doing reduced integration. So what is that I am doing? I am trying to find out the strains at the center. Now what happens? What happens to the strains at the center? 0, okay? Because what am I trying to do with these integrations? I am trying to concentrate on certain select locations. Clear? On certain select locations. So one of the select location is my Gauss point, that I mean center of the element, where because I am using that select location to be the 1/1 Gauss point. So though there is strain in this element, my concentration being at this point gives me epsilon to be 0. So what happens? Substitute it back into this expression here. So strain energy goes to 0. Strain energy goes to 0. Hence the name 0 energy modes. There is another mathematical explanation to it. We will not go into that for rank deficiency. We will just stop here the explanation, because there are a lot more things I have to talk about it. Maybe if there is time, we will come back to this term rank deficiency. Okay, by the way, I want to go further in this, but by the way, look at this, and is there anything else that is bothering you? What I am saying is that it is bending. Actually, it is this kind of deformation exists because of bending, right? It's trying to bend, okay, and you get this. Is there anything else that is bothering you in this? Go back to dig up your memory on strength of materials and tell me whether you are bothered by something else in this. Yeah, just look at this. Just look at this. Yeah, come on, that's it. No, look at this figure here. Yeah, I hear murmurs, but you can be bold. What happens to the shear? Okay. Now, what are our famous rules, okay, which we used before in our earlier strength of material classes? Plane sections remain plane. Why did we use that rule? Because plane sections we want it to remain plane, because we don't want any shear, okay, shear deformations. Okay. Now, in other words, in actuality, this bending would be like this, so that this angle would have remained 90 degrees and plane sections would have remained plane. But this kind of deformation is not possible, and hence we get something like this. Okay, that's another issue, of course, because I wanted to point out this, and this is another issue. Nevertheless, it's also very important. So now what happens because of this? You are introducing shear, okay, because this angle is no more our famous 90 degrees. Okay. So people call this also with different names, and this is one of the drawbacks, okay, what they call as parasitic shear. Okay, please note this is different from rank deficiency or zero energy modes. Why I pointed out is because many people get confused between the two. Okay, this is what we call as parasitic shear. It looks like a, a parasite which doesn't move, doesn't go off and sits there and introduces a shear, and hence it is called as parasitic shear. On the other hand, rank deficiency or zero energy modes come out because we are in the neutral axis. Okay, at the point where it is 0, epsilon is equal to 0, we go and integrate it at that point and get into trouble. All right. Okay. Now, the question that you would ask is, if you go and look at many packages, like for example, if you look at a very good package like Abacus, okay, go and do explicit codes with that. I know a few of you may be working on explicit codes with Abacus. You will see that those people have done or use only reduced integration. Okay, then is it that their results are always like this, or do they do something else? Yes, for every problem there is always a remedy. So guys don't want to leave this single point integration, for example. Okay, we will expand this list later, but let us first understand what is classical integration or correct integration and reduced integration. So what they do is, look, the results are the benefits are enormous with reduced integration. So I will do reduced integration, but they also do a repair job by doing what is called as hourglass control. They also do a repair job, or they do, they have another algorithm which also takes into account, or which also controls this hourglass modes, and call them as hourglass modes, hourglass control. But of course, hourglass control does not work all the time, okay, because of certain limitations. We will see that if time permits in the next class, or at least I want to get you to this term, hourglass control. What is hourglass control? They control this hourglassing modes, okay, by still using this kind of reduced integration with hourglass control. But it doesn't work because theoretically, though it is correct, works only for some nice elements. So one of the things that is recommended is, look, use reduced integration, but take more number of elements. That will to a certain extent sort out the problem. Now what are the effects of hourglassing? Now you know how to recognize. I hope you now have a big picture. Okay, now you know what is a big picture. There is a correct integration rule, there is what is called reduced integration rule. There are advantages of reduced integration rule, but it results in hourglassing, and how the hourglassing looks like was also shown to you. Okay, and lastly, to add to this big picture, okay, we also have what is called as hourglass control. Right? Is that clear? Okay. Now with this we will stop today, because we have to now look at expand other things, like I want to talk a few more issues on reduced integration, possibly introduce hourglassing control. That we will take it up in the next class. But if there are, I am sure that all of you are able to understand, because I have introduced a lot of concepts in this class, okay, but there is a lot of theory into it. Maybe if time permits we will cover it in the next class, and I hope you understand at least the complete big picture. Is there any questions? Okay, we will meet in the next class.